Okay, so this is the ideal gas law. The ideal gas law is an equation where we relate pressure, volume, temperature, and the amount of gas in a single equation. So, before we talk about the actual ideal gas law, we're going to talk about Avogadro's law. And Avogadro was an Italian scientist in the early 1800s, and he said that equal volumes of gases at the same temperature and pressure contain the same number of molecules regardless of their chemical nature and physical properties. Now, what this means is that regardless of the type of gas that is present, if the gas is held at the same pressure and the same temperature and has the same volume, it has the same number of gas molecules. So these three canisters of carbon dioxide, helium, and oxygen here, since they're all at the same pressure and they're all at the same temperature and they're all at the same volume, they all have the same number of gas molecules. It doesn't matter that they're different gases. They all have the same amount of gas. Now, another way of thinking about this is that if a gas is held at the same pressure and the same temperature, the only way to increase the volume, regardless of the gas, is to increase the amount of gas. So think about this. You've done this. Every time you blow up a balloon, you're holding that gas at the same pressure and the same temperature. You're just increasing the amount of gas. And what happens? You blow up the balloon and the volume expands. Okay, the balloon expands. Eventually, it gets to a point where you start to build up pressure and the balloon explodes. Okay, but during the inflation process, as the amount of gas increases, the volume increases. This is a direct relationship. A direct relationship is where one goes up, the other goes up. In this case, volume represented by V and amount of gas represented by N. As one goes up, the other goes up. We can turn this into an equation where V1 divided by N1 equals V2 divided by N2. Again, where volume is the volume of the gas and N is the amount of gas, typically measured in moles. Now, if you think about what we've done in the previous video and in this video, what we have is we have some direct relationships between different variables. Pressure and temperature, volume and volume and the amount of gas, given what we just did with Avogadro's law. Now, we also have an inverse relationship, pressure and volume. So, we could take all of these relationships and put them into one equation. And that one equation is our ideal gas law. And the form of that equation is PV equals nRT. Now, you might be saying, wait, I've never seen R before. What is R? Well, R is a constant that is used in the equation that allows us to put all these different variables, set them equal to one another. So, what exactly is R in the equation PV equals nRT? Well, if we rearrange the equation and we solve for R, what we get is PV divided by NT equals R. Now, the value and the units of R depend on the units of measure of pressure, volume, the number of moles or the amount of gas, and the temperature. Typically, pressure is measured in atmosphere, volume in liters, the amount of gas in moles, and the temperature is always measured in Kelvin. Remember, always Kelvin. If we plug those units into our expression, PV divided by NT, what we'll get is 0.0821. And that will be in the units of atmospheres times liters divided by moles times Kelvin. And that is a constant. And that is going to be the R value we are going to use when we use the ideal gas law. Now, if you change those variables, you'll change the value of R. So you'll want to make sure that whenever you use this equation, that your pressure is in atmospheres, that your volume is in liters, that your amount of gas is in moles, and that your temperature is in Kelvin. Otherwise, this equation is not going to work. It has to be in those units. Okay? So, given that idea, we can now actually apply the equation to a problem. So a hot air balloon, when fully inflated, has a volume of 2,200,000 liters at a temperature of 300 degrees Celsius and a pressure of 1 atmosphere. How many moles of gas are inside the balloon? Well, what we have here is we have a problem where we have a volume, we have a pressure, we have an amount of gas, and we have a sorry, we don't have an amount of gas. That's what we're finding for, but we do have a temperature, and we also have a constant R that we know. Our pressure is 1 atmosphere. Our volume is 2,200,000 liters. Our temperature is going to be 573.15 Kelvin because we got to put it into Kelvin. So remember, add 273 to any Celsius temperature and you convert it into Kelvin. And what we're going to do is we're going to rearrange this equation and we're going to solve it for N. So PV divided by RT equals N, because what we're trying to do is we're trying to figure out how many moles of gas are present. And now we plug our values in. We take 1 times 2,200,000 divided by 0.0821, which is our R value constant, 0.0821, times 573.15, and we solve this for N, and we should get 46,765 equals N. And given that, we can now round it to the right precision, the right number of significant digits. It will be 47,000 moles equals N. So that's a simple gas law problem. Hopefully you understand what we've talked about here. Have any questions, feel free to come talk to me, and good luck.